This is mathheals.com, where you can find more links to YouTube videos for math subjects and computer science. Let's take a look at inverse functions, and this is part one. I've split this into the algebra part and then the trig part. Now, let's first talk about some of the definitions that you've seen in the past. A little bit of review. We have a function, and this says for every x there is only one y. And that definition is pretty hard to work with. We got an easier definition. This definition doesn't work all the time, but it'll be probably 95% of the time it'll work. If you have one of the following, it is not a function. If you have a y squared, y to the fourth power, or actually y to any even power, then it's not a function. If you have the absolute value of y, it's not a function. If you have a plus or minus square root of x. Actually, if you have plus or minus x of any sort, it's not a function. If you have x is equal to a number, it's not a function. For example, x is equal to 3 would not be a function. Now we have this just covers the function part. We have a one-to-one function. And this says for every x there's only one y. And for every y there's only one x. Now that first part is the function part, and then the second part is the one-to-one part. Now this is the easier definition for a function. Let's talk about an easier definition for a one-to-one function. And it says if you have one of the following, it is not a one-to-one function. If you have an x squared, x to the fourth, or x to an even power, it's not a function, or one-to-one function. If you have a y squared, y to the fourth, or y to an even power, it's not a function. If you have absolute value of x, if you have the absolute value of y, if you got a plus or minus square root of x, plus or minus x of any sort, if you have plus or minus y, if you have plus or minus square root of y. Actually, when you have plus or minus, probably if I make the statement, if you have plus or minus anywhere in your problem, it's not a function. If you have x is equal to a number, if you have y is equal to a number, anytime you have these, it's not a one-to-one function. Unless there is a condition put on x. Let's see what I mean by that. Okay, we got y is equal to x squared. Now this is not a one-to-one function, but if I come here and I put x is greater than or equal to 0, so they're putting a condition on x. They're saying it looks like this when x is greater than or equal to 0. Well, by putting a condition on there, they're making it one-to-one. So we then, which we're going to see here in a minute, that leads into finding the inverse. A lot of different definitions here and so forth. We got a horizontal line test. We had a vertical line test that said if any vertical line intersects your graph at two or more places, it's not a function. What this checks is it checks to see if the one-to-one part is true. So this says if any horizontal line intersects the graph at two or more places, it is not one-to-one. And we're going to go be looking at examples at all this, so, but hopefully this isn't brand new. You saw this in college algebra. Let's see. Well, why is this important? Why do we care? If a function is one-to-one, it has an inverse. So if a function is one-to-one, it has an inverse. If it's not one-to-one, there's no inverse. If it is not one-to-one, then no inverse. Well, what is an inverse? And this first definition we're going to take a look at here is an algebraic definition. And we got two functions, f and g. F and g are inverses if the composition of f and g is equal to x and the composition of g and f is equal to x. Both of them have to be true. And that's how you determine algebraically if two functions are inverses of each other. Let me save this. And slow. There it goes. And okay, this would be Calc 1. Inverse functions. Part 1, page 01.pdf. There we go. Well, let's take a look at some examples now. f of x is equal x to the third minus 5, and g of x is equal to the cube root of x plus 5. And it says show that f and g are inverse functions. And the first part says analytically. That's algebraically that we looked at in the previous page here. So first thing we're going to do is find a composition of f and g. Well, that's the same as f of g. And this is just evaluating a function. So we're going to take our f of x, which is x to the third minus 5. Where x is, we'll put in parentheses. Everything else remain the same. And whatever is inside the parentheses right here is what we're going to put in down here. So we're going to put g in there. But g is equal to the cube root of x plus 5. So then this becomes the cube root of x plus 5 to the third power minus 5. Now when your index, and that's the index is a number in a slot, when your index, which is 3, matches the power, then they cancel each other out along with the radical. And we're left with x plus 5. So we got x plus 5 minus 5. And 5 minus 5 gives us x. So that's the first part. That should be equal to x. Okay, second part. Let's find a composition of g and f, which is g of f. We're going to take our g of x. Wherever there's an x, you put in parentheses. So we got the cube root of parentheses plus 5. And again, whatever's inside the parentheses right here is what we're going to put in right here. So we're going to put in f there. So we got the cube root. And f was x to the third minus 5. So we plug that in now. Negative 5 plus 5 cancel. And you get the cube root of x to the third. Now notice my index here is 3 and the power is 3. Doesn't matter if the power is on the outside like this first part or the inside like this. They cancel each other out. So this gives us x. Since these are both equal to x, then that means these are inverses. Now graphically. Well, graphically, let's talk about what we're looking for. Now x to the third minus 5. That's the graph of x to the third, and the minus 5 means it's been shifted down 5. And I'm going to kind of roughly do it here, and then we'll talk about how to do it on the calculator. That'll be a little bit easier. Now, the cube root of x plus 5. Well, the cube root of x, we know what that graph is. When you got the number inside with the x, then it's shifted left to right opposite what you think. Plus 5 would make you think it goes right 5, so it really goes left 5. So we got 1, 2, 3, 4, 5. And so this one right here is our g of x, and this other one is our f of x. Now here the line going through the center here is a line y is equal to x. And I didn't draw this real well. You can plug these in the calculator and see this a lot better. But for two functions to be inverses of each other, they have to be symmetric to the line y is equal to x. So let me put that note here. So inverse functions are symmetric to the line y is equal to x. That's always best to show an example when you're talking about that, because you can see it a lot better. Well, what that means is that I can take this piece of the graph right here and I can flip it across this line and it would land on this piece. I can take this graph right here, this blue part, Flip it across this line, and it should land on this piece. Now, I say should because you see I didn't draw it real well, but you can see it is symmetric to the line y is equal to x. So they're inverses graphically. Now, if I were to plug this in my calculator, let me just show that. If I come here, press y equals, press clear if you have something on y1, and x to the third minus 5. So I'll do x key caret 3 minus 5. Then I'll do a down arrow to go to y2, press clear if you have something there. We want the cube root of x plus 5. So press math, and the cube root is the fourth one, so I'll press 4. And then x plus 5. And then closing parentheses. And now if I graph these, by pressing the graph button, you can see a lot better that they are truly inverses of each other. Okay, let's look at our next problem. Same instructions. Got f of x is equal to 2 over 3 minus x, and g of x is equal to 3x minus 2 over x. Okay. And this one isn't so easy to graph by hand. These aren't basic graphs we've seen in college algebra, so I'll strictly go to the calculator on these. But let's do it algebraically first. We have to find the composition of f and g. Remember, that's f of g. So we're going to take our f of x, and wherever we have an x, we'll put in parentheses. So we've got 3 minus parentheses. Now, whatever is inside the parentheses right here is what you put inside the parentheses down here. So we're going to put g in there. But g is equal to this 3x minus 2 over x. So let's put that in there. Well, we're trying to see if this is equal to x. Well, we can get rid of the fraction inside the fraction. That's complex fraction. Specifically a complex rational expression when you got x's. But you do that by multiplying everything by the LCM of all your inner denominators. The only inner denominator we have is the x, so multiply everything by x. So multiply the top part by x, the 3 by x, and the 3x minus 2 over x by x. Now when we do that, this x here is going to cancel with that x. And we got 2x over 3x minus, and then inside of parentheses we got 3x minus 2. This negative right here has to flip the sign of everything inside the parentheses. That's why I kept the parentheses there. So that gives us 2x over 3x minus 3x plus 2. 3x minus 3x drops away. Got 2x over 2. The 2's cancel, and we got x. So that's good. That's the first piece. Second piece, we want to find the composition of g and f, which is g of f. We'll take our g of x, which is 3x minus 2 over x, and everywhere we have an x, we'll put in parentheses. Again, wherever I have the parentheses, I'm going to put in f. So I'll put f here, and I'll put f here. Whatever's inside the parentheses here is what you plug in the parentheses here. But f is equal to 2 over 3 minus x. Plug that in. This one won't be as simple to work with. 3 times 2 is 6, so we got 6 over 3 minus x minus 2 over 2 over 3 minus x. Now we need to get rid of the complex fraction, so we're going to multiply everything by the LCM of all our inner denominators. We have 3 minus x, we have 3 minus x. They're both the same, so our LCM would be 3 minus x. So we're going to multiply everything by 3 minus x. we go. Notice I multiplied times this first fraction here, times the -2, and times the fraction on the bottom. Now these 3 minus x's cancel here. These 3x minus cancels. 3 minus x cancels there. I'll learn to speak someday. I got 6. -2 times 3 is -6. -2 times -x is positive 2x over 2. 6 minus 6 drops away, and we got 2x over 2. 2's cancel, and we got x. So they're both equal to x, and if they're both equal to x, once you find the composition, that means they're inverses. Well, let's graph this. So the key to graphing, this is a rational function. Rational means single fraction, and you have x's. The key to it is if you have more than a single variable or single number in top or bottom of your fraction, you have to put parentheses on it. So when we plug that in, we're going to put parentheses around the bottom here, and on our second one, we'll put parentheses around top. Now here's a single 2, here's a single x, so we don't need to worry about it there. Let's see what this looks like. Press y equals, press clear, and I got 2 divided by, beginning parentheses, 3 minus x, closing parentheses. Now down arrow, press clear on that. And we've got 3x minus 2 inside of parentheses, so beginning parentheses, 3x minus 2, closing parentheses, divided by x. And then graph. Not so easy to see. Let me come up here, press y equals. I'll make one of these bold. So I'm going to left arrow over, and see how my flashing cursor's on the equals here? I press it one more time, and it puts it on the slash. If I press enter one more time, or press it one time, change to thick slash. Now if I press graph, you see this part right here, that's looks like symmetric to the line y is equal to x with regards to this. And this piece up here is symmetric to this thick piece down here. So it is indeed in inverse graphically. Now if I press y equals, let me show you how to clear this out. If I press clear, down arrow, press clear. On the older TI-84s, TI-83, this is okay then. This is back to where it was. On newer TI-84s, you have to actually manually set it back. It's kind of a pain. If you press your left arrow key twice and put your cursor on here, and you keep pressing enter until it's a normal line again. There we go. And that's how you set it back. Okay, now this one's asking us to find the graph of the inverse. Come down here, see if I have room. Okay, let me save this. Date. There we go. This will be page 2. And then it goes off like that. Okay, that's our graph. And it says find the graph of the inverse. Well, we've already talked about this. The graphs are symmetric to this line. The line is y is equal to x. So I'm going to take this graph and flip it across that. You notice how this starts at 2 on my x-axis. My inverse will start at 2 on my y-axis. That's how it flips. If I look at this point here, right there, is 2, 0. So my inverse is going to have a point 0, 2. So it'll be right here. They flip. The point here just flips the whatever it is. If this was 5, 3 up here, this would be 3, 5. And I'm going to eyeball this. I'm not that great at these. It's probably as good as I'm going to get. This would be our answer. Now, usually they get away from writing as F and G, and they start putting the inverse notation. The inverse notation looks like this. Looks like F to the negative 1 power. But that would be our answer. Now these next ones refer to the horizontal line test. And if you remember the horizontal line test, it says if any horizontal line intersects your graph at 2 or more places, it is not 1-to-1. Now it might still be a function. So let's see how to use that horizontal line test to work this problem. Okay. There's our graph right there. It says use horizontal line test to determine whether the function is 1-to-1 and therefore has an inverse. Well, the question is, can I draw a horizontal line that intersects at 2 places? 2 or more. Well, this one's just 1. This one's just 1. No matter where I drop a horizontal line, the most it'll intersect is 1 place. Which means that this is 1-to-1. And this symbol here implies. So this implies that it has an inverse. Let's look at another one of those. I probably won't get this right. You get the idea, though. This. Close enough. The reason why I say it's close enough, it's obvious. If I drop a horizontal line here, same instructions. Well, this right here intersects at 2 or more places. Since a horizontal line I draw on there intersects at 2 or more places, that means it's not 1-to-1. So, no inverse. Now these examples gave us the picture. This next one, we're going to actually have to graph it ourselves. Okay, so number 6. Now we got f of x is equal to x squared over x squared minus 2. Rational function. Key to, again, putting a rational function in your calculator is put parentheses around top or bottom if there's more than a single variable or a single number. X squared is actually would be considered like a single variable. They're kind of tied together. It's not single term, because if I had 2x squared up there, I'd have to put parentheses around it. Okay, so I'm going to come here. I'll press my y equals, if I'm not already there. Press clear to clear wherever's not in line. We got x squared, so press the x key, press the x squared, divided by, beginning parentheses, then x squared minus 2. TI3, TI4 is very forgiving about closing parentheses at the very end. I'll go ahead and put it there just for to be complete. And now press graph. Okay, so that's our graph. Doesn't have to be perfect because I think you can see what's happening here. So the question is, off this is determine it's 1-to-1 and therefore has an inverse. Well, is there any place I can draw a horizontal line that intersects at 2 more places? Well, there's a lot of places. If I drop one here, it's 2 more places. If you find any horizontal line that intersects at 2 or more places, that means it's not 1-to-1. So no inverse. Not that I can spell. Try that again. So no inverse. Now remember, I put up a list earlier on the previous page that said if you have x to an even power, it's not 1-to-1. So right away, seeing this x squared, I wouldn't even have to look at the graph. I know it's not 1-to-1. I don't even need to graph it. And that's what these next ones revolve around, is just looking at it and seeing if you see any of those bad items that I had written down. And let's look at this problem. f of x is equal to x to the third plus x minus 4. And it says determine whether the function is one-to-one on its entire domain and therefore has an inverse function. Well, we can have x to an odd power, we just can't have x to an even power. So this one's actually okay. This is one-to-one, which implies it has an inverse. Let me show you another example. I think I only had one in the PowerPoint there, but if I say I had 3 minus x to the fifth plus absolute value of x. Remember, from our list, we said we can't have absolute value of x or absolute value of y. So this is not one-to-one, so there's no inverse. Let me save this page. And let's look at finding an inverse. Now the assumption is that it's one-to-one. So finding the inverse of a function. I'll put that up here at the top. The function must be one-to-one. Step 1. Replace f of x with y. Step 2. Interchange x and y. Swap them. Step 3. Solve for y. Step 4, replace y with our inverse notation. And step 5, if necessary, make our inverse of f one-to-one using the graph. Graph is usually the easiest way to make something one-to-one, if it isn't already one-to-one. We'll find these first ones are one-to-one. So let's look at this one. We got f of x is equal to 9x plus 2. Instructions say find the inverse function. Started on making this video and didn't put anything to drink in my room here. I'm dying. Okay. Anyway, I'll quit whining. This is one-to-one. Step 1. Reason I know it's one-to-one, it doesn't have any of the bad stuff. Doesn't have x squared, x to the fourth, x to an even power. Doesn't have y squared, y to the fourth, y to an even power. Doesn't have absolute value of x, absolute value of y. Doesn't have plus or minus square root of x, plus or minus x, and all those. Okay, step 1. Replace f of x with y. So we got y is equal to 9x plus 2. Step 2, interchange x and y. So we got x is equal to 9y plus 2. Everywhere you had an x, you put a y. Everywhere you had a y, you put an x. I said that right. Never sounds right when I say that. Step 3, solve for y. I'm going to take the 2 over. So I got x minus 2 is equal to 9y. And I'm trying to get to y by itself, so we'll divide both sides by 9. So we got x minus 2 over 9 is equal to 9y over 9. Or x minus 2 over 9 is equal to y. Step 4, put your inverse notation in. So inverse of f is equal to x minus 2 over 9. Now they might put this in slope-intercept form. This is one-to-one. Doesn't have any of the bad things in the list, so that's our answer. We don't have to do step 5. Let's take a look at this one. These are kind of nice because you know, it's just like, well, how often do you use an inverse function? They're kind of nice for the beginning of calculus because they refresh your memory on all the different techniques for solving. Well, this is 1 to 1. We can have x to the third. We just can't have x to an even power. Step 1, replace f of x with y. So we've got y is equal to x to the third minus 2. Step 2, swap your x's and y's. So we got x is equal to y to the third minus 2. Step 3, solve for y. I bring the negative 2 over, becomes a positive 2. Now this is the same as x plus 2 is equal to y to the 3 over 1 power. Now from college algebra you studied the power principle. The power principle said you can take both sides to a power, basically. And to get rid of this this 3 here, you'll take both sides of the reciprocal of 3 over 1. Reciprocal is fraction flip. So I'm going to take both sides of 1/3 power. Like that. And 1/3 power is the cube root. So this is the cube root of x plus 2. Now over here, these 3's would cancel, and the 1's would cancel, though 1's are trivial. It would be left with y. Now, when this was in fraction form, the number on top was odd. Since this was odd, we didn't need to put a plus or minus on the other side. But if this number on top was even, we would need to put a plus or minus over there. Step 4. Put your inverse notation in. So the inverse of f is equal to cube root of x plus 2. We still don't have to do step 5 because this is 1 to 1. We can have the cube root of x plus 2. That's no problem. Okay, let's look at this next one. Got f of x is equal to square root of x minus 3. Well, this is 1 to 1, so we're fine there. Step 1, replace f of x with y. So we got y is equal to square root of x minus 3. Step 2, swap your variables, swap your x's and y's. So this becomes x is equal to square root of y minus 3. Step 3, we wanted to solve for y. And this is a square root. If you remember solving square root equation or equations that contain square roots, you get the square root by itself, and then you raise both sides to a power equal to the index. Index is the number that's in the slot right here, and we've got square root, that's by default 2. So we'll square both sides. So we'll square the x, and we'll square the y minus square root of y minus 3. So we've got x squared is equal to y minus 3. Again, when the index matches the power, they cancel each other out. Take negative 3 over, and we got x squared plus 3 is equal to y. Put our inverse notation in, step 4. So the inverse of f is equal to x squared plus 3. Now step 5 was, if necessary, use a graph to make it 1 to 1. This is not 1 to 1. It has an x to an even power. We can't have x to an even power. Let's look at what in the world this graph is anyway. Square root of x, we know what that is. That's that graph that looks like this. Now, if you put a number inside with the x, it shifts it left or right, opposite what you think. The negative 3 would make you think it goes left 3, so it really goes right 3. So there would be our graph. Now we know the inverse is symmetric to this line y is equal to x. And since this starts at 3 on the x-axis, my inverse will start at 3 on the y-axis. So this is what my inverse is going to look like. That would be my inverse. This is our function, of course. What we came up with, if I look at this graph, y is equal to x squared plus 3. We know what x squared is. Plus 3 shifts it up 3. So what we came up with was this right here. Well, look at what we want. It looks like we want the right-hand side of that. And that's the key on this one. To make this one 1-to-1, we have to put a condition on x. So this is going to be, the right-hand side is where x is greater than or equal to 0. And that'd be our answer. Let me save this. A bad idea to start this recording with nothing to drink. Be a few bricks short of a load here. I have to remember that next time. Time for my tablet to blow up. Okay, let me bring up a new one. There we go. Okay, let's look at this one. F of x is equal to square root of x squared minus 9, and x is greater than or equal to 3. If I were to plug this into my calculator, trying to think what in the world it would look like. Hey, let me go look. I'll blame it as being a long day. And y equals clear, and this is square root. So I'll do second x squared, and then we got the x key, x squared minus 9. And graph. Ah, that's what it looks like. Okay. Go off looking like that. Now, the reason why it puts a condition on here, and that's why I wanted to show it, is if I look at my original graph here, it fails a horizontal line test. If I draw a horizontal line here, it'll intersect at 2 or more places. That's why we have to put a condition so we don't look at the right side. Okay, it is 1-to-1 based upon looking at the graph. So let's go through our steps. First step, replace your f of x with your y. Step 2, interchange x and y. So we got x is equal to square root of y squared minus 9. Step 3, solve for y. So this is a square root again. So got square root by itself, so we'll take both sides of the second power. There we go. I'm going to do that. This gives us x squared. Over here, the square root and the second power cancel each other out. So we've got y squared minus 9. Take negative 9 over, and we got x squared plus 9 is equal to y squared. Square root property. If you got something squared equal to the other side, you drop your squared, and you put a plus or minus square root around the other side. So we got plus or minus square root of x squared plus 9 equals y. Step 4, put our inverse notation in. So we got the inverse of f is equal to plus or minus square root of x squared plus 9. Now there's a problem with this right here. If I was just double checking to make sure I did my algebra right. If I take a look at this, it has a plus or minus x of some sort. We can't have the plus or minus, so this is not 1-to-1. So step 5, we need to figure out how to make it 1-to-1. Okay, now this is our function right here. We know that the inverse is going to be symmetric to this line, y is equal to x. This starts at 3, so my inverse will start at 3. And try to roughly sketch it here. That'd be our inverse, more or less. Now, now here we got a plus or minus. Well, having the inverse notation here, this is the same as y. So basically we're saying y equals this. Well, up here, y is positive. So we can drop the plus or minus and just have this right here. Okay, now there's a problem with this. Let me go graph this and show it. Calculator is so wonderful for seeing this stuff. We'll press y equals, press clear. We got the square root. Oops, try that again. Okay, so press y equals, press clear. I'll do second x squared, then x key x squared plus 9. Closing parentheses if you want, and then graph. I didn't draw that real well, but you get the idea. Looks like I'm only keeping the right side here, aren't I? This has both sides, which definitely is not one-to-one because it fails the horizontal line test. So we have to, again, put on our condition here. Now, our condition here would be that x is greater than or equal to 0. And this would be our answer. Okay, let's look at our next one. Got the cube root of x plus 2. Well, this is one-to-one. There's none of our items that were in that list. You know, x to an even power, y to an even power, plus or minus x of some sort. So let's just go through our steps. Replace your f of x with y. Step 2, interchange x and y. So I got x is equal to the cube root of y plus 2. Step 3, solve for y. Well, when we got the cube root of y plus 2, that's the same as y plus 2 to the 1/3 power. We're trying to get rid of that exponent there, so we're going to raise both sides to the reciprocal of it, the power principle. So take both sides of the 3/1 power, or the 3rd power. Now take both sides of 3/1, these 3's cancel, the 1's cancel, then we'll be left with y plus 2. So we got x to the 3rd equals y plus 2. Now, since when I wrote this in fraction form, I had 1/3, the number on top is odd. That means no plus or minus. We didn't need to put a plus or minus on the other side. Now take 2 over, so we got x to the 3rd minus 2 equals y. And step 4, put our inverse notation in. So the inverse of f is equal to the x to the 3rd minus 2. Now there's no need to do step 5 on this one because x to an odd power is okay. We just can't have x to an even power. Let's save that. And let's look at our last problem. F of x is equal to x to the 2/5. X is greater than or equal to 0. Why did they put a condition on this? Well, let's graph this and see what it looks like. The key, if you got more than a single number or a single variable in your exponent, you had to put parentheses around it. So when you plug this into our calculator, we're going to want to put parentheses around the exponent like that. So we got y equals, clear, I'll do my x key, caret, beginning parentheses, 2/5, so 2 divided by 5, closing parentheses, and then graph. You'll notice it fails the horizontal line test. I can draw a horizontal line here that intersects at 2 or more places. That's why we're only looking at the right-hand side, where x is greater than or equal to 0. So what we're looking at, see if I can sketch this halfway decent. We're only looking at this piece right there, which is 1-to-1. Okay, let's go through our steps. Step 1, replace your f of x with y. So we got y is equal to x to the 2/5. Step 2, interchange your x and y. So we got x is equal to y to the 2/5. Now we want to get y by itself. Step 3, solve for y. We're going to take both sides to a reciprocal of this. We got 2/5. The reciprocal of 2/5 is 5/2. So we're going to take both sides of the 5/2 power. Like that. And then over here, we'll have y to the 2/5 to the 5/2 power. Now notice, when we got this in fraction form, our number on top is even. If the number up on top is even, then you need to put a plus or minus when you do that power principle. So we're going to put a plus or minus on this other side. Now if the number is odd, you don't need to put the plus or minus. Okay. These 2 is going to cancel. These 5 is going to cancel. And we've got y is equal to plus or minus x to the 5/2. Step 4, put our inverse notation in. So put our inverse of f in is equal to plus or minus x to the 5/2. There's a problem with this. We can't have a plus or minus x of any sort. That's not one-to-one, so we need to make it one-to-one. Well, let's look at our graph here. This is our f of x. Here's our line, y is equal to x. Our inverse is symmetric to that, so I take this graph here, flip it across that, reflect it across that, and it would look something like this right here. Think what this is saying. Our inverse notation is the same as y on this side, so we're saying y is equal to plus or minus x to the 5/2. Well, think what your y values are right here. And again, the blue here is your inverse. The y values there are positive, aren't they? So I'm going to drop the negative, and our answer will be equal to x to the 5/2. Maybe. Let's go graph this and see what in the world it looks like. Because sometimes when it comes up weird like this, maybe we need to put additional restrictions on this. Blind, click the wrong thing. Watch that blow up my machine. Oh, I'll be mad. Go away, Adobe. Caret. Yeah. Go away. Okay. X caret, and put parentheses around the exponent, 5/2. 5 divided by 2, closing parentheses, graph. Okay, well that looks like all I got, which is what my inverse is. So this is fine as is. We don't have to put any kind of restriction on what x is equal to. Let me save that, and I think that's yep, that's the last one. There we go. And now let me stop the recorder.